Actually, still the problem is there is a little inconvenience, and I did not get actually the permission to go to Sarawak, travel to Sarawak. So I will be delayed by 1 more week. So the lab next week will be your teaching assistant will be there. Your teaching assistant will be there, but I will be connected through this online class. And then from the lab 2, experiment 2, hopefully, if everything goes fine, I'll be there in the lab physically. All right, so this is announcement. I will announce it once again through the Canvas site. And week 3, we will start the online quizzes. So the quiz will be automatically, the link for the quiz will automatically be there in the Canvas thing. Did anybody just raise their his or her hand? I see at a glance, but I did not quite get who was it. Anybody want to ask any question on that? No. All right. So accuracy and precision. By the way, we are still learning about the process of gathering our data and calculating and making the measurement correct and all those things. Especially it is still for the calculation, and much of it will need to do the lab report preparation and for the calculation or discussion at the end, of course. But it will be useful when, I mean, the knowledge from here will be useful when we do the calculation for our calculation part of our theoretical questions in the experiment. Sorry, in the exam. So this type of significant figure, tolerance, uncertainty, standard values, the mean, all those things we have to take care, because there will be marks embedded or for this type of calculation, even though it is not mentioned in the question, but you know, this answer got this type of mathematical figures, so you have to be aware that there will be this type of consideration: accuracy, precision, tolerance, uncertainty, mean values, standard deviations, all those things when it is in place. Not for all the questions, but yeah, some of the question. It is hard to understand how and when, but if we go through the problems through the tutorial and also for the practice questions, then you will understand where and how we should use this type of knowledges. Okay, so accuracy and precision. How does it help when we are using this concept of gathering the data or measurement for our experimental work? Sometimes this is a dart board, right? We know this is a dart board, these are the darts, and this is the bull's eye. We call it bull's eye, I think, and you know it. So when the dart hits the bull's eye, it is a very good, you get the highest score, right? Away from that bull's eye, you lose the point if you go for the dart game. So by this way, we can show that how accurate your result is. If it is hitting this bullseye, this is much accurate. That means you are hitting the main point. But sometimes we will not be able. Not everyone. It is not our fault per se. Maybe it is a instrument fault, or the methodology's fault. But nonetheless, we will get at some point this type of result, that all our darts are hitting at the same position, which is away from the bullseye, which is away from the accuracy, right? That means this is not my fault. There is some problem, or maybe it's my fault. That is something problem. But whatever I'm doing, I am very much I'm very much precise in what I'm doing, right? Although it is not accurate, but very precise what I'm doing. That's why all the darts are at the same place. At some point, you will get not the bullseye, but near the bullseye. This is precision is low. That means the darts are away from one another. It is not hitting at the same position. It is not hitting at the same position. It is away from one another, but it is all of them are near to the bullseye. That means near to the real value. It is near to the real value. That means it is highly accurate. I mean, quite not high accurate, but it's quite accurate, but precision is very low. That means we are using different methods, or we are not, what do you call it? We are not, don't disturb me. We are not standardized in our methodology, probably, or our instrument, but it is quite near to the accurate value. So this is low precision, but this type of results are okay, is acceptable. All right, but this type, number one, this is number one, this is number two, this is number three. This number one type of results are not usually is acceptable. They will say, okay, you have done good, your methodology had problem, or you had problem, but it is not, I mean, you tried best, but it is not accurate. Although it's very precise, it's not accurate. But for this number three, number third, we'll see that it is all are very highly accurate, highly precise, and it is like a textbook example of accuracy and precision. And in real life, we usually do not see this type of result. Okay, we usually do not see this type of results, and this is when it is happening. This is, we know that these are to some extent it raises our concern that how should you get this 100 over 100, right? So anyway, but sometimes we get it. We can achieve this type of result if we are very much careful, if we are very much devoted to the work, and if it is all the materials, the methods, the instruments, time and space are on our side, then of course we will get this type. It's not impossible. We get it. We sometimes we get this type of result as well. But most of the time in our experimental work, two prevails. The situation two prevails. So there are two things is coming here: systematic error and a random error. So these two things, I'm not sure whether you are introduced to this thing, are familiar to two of these terms, but we'll talk later on what is systematic error, what is a random error. All right, now better I talk now. Systematic error is giving us by the system, or we are the problem. There is a problem that we have in our methodology, or by the person it is doing the work, or with the resources or the materials or the instrument. Anyhow, there is the problem. That is the systematic problem, error occurring by this. But the random error that occurs, and systematic error we can actually rectify. We can reduce the systematic error, or we can eliminate the systematic error by doing it over and over again, or try to understand why there is a problem or how it could be done more accurately. All right, but there another thing is a random error. Random error that we do not have control over. All right, we do not have control over, like we are using the electric balance. All of you have seen the electric balance in the lab. You put the materials on the balance will give you some result, some reading. But this electric balance depends on the electric voltage. Right? It depends on the electric voltage. If the voltage is fluctuating, that is beyond our control, to some extent, it is a random error. It will give you a random error, and it is giving both sides. It is not only increasing the voltage. The voltage may also reduce. So the reading in this case, probably we will get on the both side, right? This is a positive area, this is a negative area. So if the voltage is increasing or decreasing, it's possible that we will get positive value or more result or more measurement values of the measurement, or to some extent less of the value of the measurement. So it happens. Or sometimes in the lab we are working and then there is a sudden pressure drop, ambient pressure drop. So if this ambient pressure drop, what will happen is probably the more of the sample will be vaporized. Probably, I'm just giving an extreme cases example that how it can happen. Or the high pressure or low pressure. So it will also increase and decrease the temperature for the measurement. So it is beyond our control. We cannot control the ambient pressure to stabilize or the voltage to be perfectly stable, although you can use the stabilizer, but to some extent it fluctuates. It's not harmful, but it fluctuates. So these type of things are the random error, and it can happen on the both sides. You can get a positive value of the measurement or negative value of the measurement. So that is a random error, and that is how random error, it is very hard to remove it. But if we again use a different time, different instrument for the same measurement, then probably we can reduce the random error, but we cannot eliminate totally. Systematic error, probably we can eliminate if we do it. Now there is a percentage of error. If we know the absolute value of the instrument of that measurement, right? Absolute value, like we are measuring 5 grams of the sample. All right, I'm saying that I'm a demonstrator in the lab. I'm giving you 5 grams of the sample. I'm asking you that measure it, see how much value do you get. Some of you getting 4.99, some of you 5.01, right? So this is the experimental value that you are getting. So if your value is not exactly what I am giving you, and most of the time, sometimes, not most or some, but usually it happens that we do not get the exact value, what it's supposed to be. And why don't we get the exact value? There are so many considerations, so many cases that, things that can occur in the lab, that it is very hard to get the exact value, right? 100 of 100 is very hard. But how much is our difference? How much is the error that we get from it? If we know the percentage of error from our measurement, we should know the true value. That means that it's 5 grams or 5 meters or 500 balls of that marbles in there, or 5 milliliter of the sample. We must know how much is that, then only we can find the percentage of error. And this is a mode value. It does not matter whether your experimental value is more than the true value or less than the true value. You will always get a positive result. It will not be negative. So the percent of error is always positive, and percentage 100%. So we will get is positive value. Okay, so percentage of error, if it is more, usually it is 5% or less is acceptable, but 5% or more, it will raise the concern that, okay, probably there was something wrong. I mean, terribly wrong. That's why it is more than 5%, and it is very hard to convince the community to understand, accept that is more than 5%, unless you have a very strong reason. You can show the reason, of course. There are sometimes more than 5% error. Then if we can explain why it is more than 5%, it should be okay. But usually I'm saying that 5% or less is acceptable. Now, 8 foot long, all right, the 8 foot long pole, and we are measuring it. Let's say 5 students are measuring with the 5 different, they have the ruler with them, and they're measuring the 5 of them individually measuring that 8 foot long pole. and they are getting 95.31 inch, 96.44 inch, and so on. So what would you report at the total length? Right, 5 of you in the same group, and each of you have measured, and you are getting it different result. None of you conformity with other, but how do you express the result? How do I express the result? Of course, it will be mean result. So 5 of us will sit together. We say, okay, your result is this, my result is this. So let's just sum it up and then divide by 5 to get the mathematical mean. That is the mathematical mean, or called the average value, and it is acceptable. Okay, it is this way. Sorry, not this one, but this average, mathematical average, this is the formula. It is acceptable. Most of the time we will do it. Okay, so this shop is selling cabbage or 4 ringgit. That shop is selling cabbage as 350 ringgit or something like that. So 5 shop we surveyed, and then we come out a term that altogether is in Kuching. The cabbage price is 3 ringgit 90 cents. Right? So that is acceptable. It is in between. So this is the average. But how much is it different? How much is different? Of course, we have to express in 4 significant figure, because we have taken the measurement in 4 significant figures. All of us have taken 4 significant figures, so the final result should be expressed in 4 significant figure, not 5 significant figure. Although we got it 5 significant, yeah. So it should follow the raw data that we have taken. Okay, so you may ask that what if somebody is taking 5 significant figure until 5 significant figures, right? If we are using different ruler that has a different tolerance, then probably we will get a different significant figure values. But again, we will follow the lowest number of decimal places, and thus how many significant figure it has. All right. So if somebody measured that 95.3 or 95.8, like that, somebody resulted, and his or her ruler only can have the uncertainty of positive point plus minus 1, then it is 95.8. So our final result should follow these 3 significant figures. All right. So this is the rule that we have seen before the previous class. Assume the pole is exactly 8 foot long, whether it is accurate, this result, how much accuracy? We see that it is not 8 foot long. 8 foot means 12 times 8 is 96 inch. It was supposed to be, but we are getting 95.9. So what is the percentage of error? Accuracy percentage of error is 0.1. So it is considered okay. It is considered acceptable accuracy. So 96, the true value is 96 inch. Our experimental value is 95.9 over 96 times 100%. It will give us 0.104%. So which is acceptable. Now, single measurement. It says that to estimate the uncertainty in a single measurement, you can use tolerance of measuring the instrument for a single measurement. All right, for an analytical balance with a tolerance of 0.0001. So our uncertainty is this. When we express the result in this way, we understand that our uncertainty is 9.0547 plus minus 0.0. So it may be 9.0547 or 49. All right, 9.0540 until 49. It can range in between, any result in between that. It will be uncertainty. We understand, right? For a single measurement. For another single measurement, this is not related to this one, the analytical balance and the bulb pipette. So for bulb pipette, our uncertainty is 0.02 milliliter uncertainty. So we understand that our value of the liquid in the drawn by the bulk pipette could be 25 milliliter or 25.0 until 25.09 millimeter, in between that range. So it should be fine. All right. So this is the tolerance of that, and so on for the burette as well. But what will happen? Okay, so this is tolerance is this, so we will 0.05 centimeter tolerance for an iron bar ruler. So we will express 28.00 plus minus 0.05. All right, so this is our tolerance. 0.05 means we have to take another 0.2 digit after the decimal places, because there are 2 digit in uncertainty. So it will automatically be 20. You cannot write 28. You cannot write 28 plus minus 0.05. That would be wrong. That would be, oh, so difficult. 0. It would be wrong in this way. Okay, this way it will be wrong. You have to express the decimal places up to the main value plus minus the tolerance. So the length of iron bar can be between 0.28 75 to 28.50 in between. Okay, so now uncertainty is 0.2%. Anyway, so repeated measurement. When we have a lot of measuring data, like we are measuring, is there any questions so far? I cannot see the main chat box. Now I am on the, I am here. No, so far no. Okay, but if you ever is a question, please raise your hand. But I cannot see the chat box here on MS Teams. I am on this PowerPoint slide. So just please unmute or give me a ping somehow so that I know that you have a question. Okay, so repeated measurement. If we have a measurement just like the pole, 12-inch or 8 feet long pole, or sometime, most of the time, we will see that we have to measure a lot of same measurement for many times. All right. So in that case, how should we come to terms with the number of values that we have? All right. How do we estimate the result, that measurement that we have done, the uncertainty of the measurement that we have just done it? So the for the main values that we have done it, standard deviation is good way to find out the uncertainty of the whole measurement. Like we have 10, 15, 20 values or more than that. Usually for standard deviation, 6 or more data sets are good to get the standard deviation, but less than 5, it is not always good to do the standard deviation, but still we do in the lab, because with we want to see the student can understand or use this type of the data or this value to do the calculation. So standard deviation is good on doing to know the uncertainty when there are a lot of data. All right, because if there are different approach to get the total uncertainty for a whole bunch of data. All right, we are coming there. I don't need to talk now. Okay, so standard deviation is one way that we should try to find out what is the measurement, uncertainty in the measurement. And this is the formula for standard deviation. This is how much of the data, let's say this is not accurate, is not perfect. What I'm going to give you a infographic, but it is to some extent, probably it will be helpful for you to understand. I have data, these dots are data everywhere, right? and then it is not in any pattern, not in a regular pattern. So standard deviation will tell us that how much these values are deviated from each other, from one another, how much it is deviated. All right. And there is another deviation, there's average deviation. We will go there later on, we will see. So just be informed that there are two types of deviation. You can see standard deviation. For our case, we will be needing standard deviation and average deviation. Standard deviation, it is represented by S, and the formula is the D is the difference between mean and value. Like we have 6 or 7 sets of data, 6 or 7 data. Hold on a bit. We have 6 or 7 data. And then we want to know the, we want to know the deviation from all of these data from each other. So what we'll do is we will take the mean of that 6 or 7 data, mean of those 6 or 7 values, and then I will deduct the mean, each value from the mean. So, and then there is, I think, yeah, here it is example for the standard value. Okay. So standard value, standard deviation, in that way we can calculate. And then relative standard deviation. Relatively, how much this data is deviated relatively from each other. So standard deviation is telling us in general sense that how much all these data are deviated from each other in this set of data, in this set of collecting the data. But when we are taking this relative standard deviation, so it is finding a relation that, okay, this is A and B, these two data. A and B is two data. So A and B is deviation to A and C. The relatively how much they are deviated, or B to D. This is D, let's say this is a D. So in this way, how much relatively they are deviated, and it will give us the percentage. In percentage, whether how much is deviated. And also standard error, we can find out by the total number, the root over of the total number of the data sets over the standard deviation. We can find the standard error for this. Okay, so for a sample of potassium chloride, all right, were weighted to yield the following results. Mass of potassium chloride is used, and we get 16.37, 16.29, 39, 35. So all these things. So what is the mean value that the mass of potassium chloride? Potassium chlorate. Okay, what is the mean value of potassium? This is perchlorate, probably potassium perchlorate, KClO, potassium perchlorate. What is the mean value of potassium perchlorate? So this one, what we'll do is we will just sum it up all together. We'll find how much is the total value, and then there's 4 sets of data, so divided by 4. The total value is divided by 4. So we will get the mean value, the average, which is called mathematical average or mathematical mean as well. And the standard deviation. Now we will go to the standard deviation. So first of all, we have done the average, which is 16.35, and the standard deviation is this, each of the value 16.37 minus this 16.35, and the value is squared. The value is squared altogether, and then this is the sum This is the sum of the next set of values. Same. We take the second one here and then deduct the average from that second value, square the total value. Third set of value minus the average value and square the value. So in this way you get, and divide for standard deviation. For average deviation we divide it by 4. But for standard deviation, we divide 4 minus 1 less than the total number of data we had. So that is 0.43. That is the standard deviation, is 0.43. So when we express the result, all together, we will write 16.35 plus minus 0.043, 0.04 should be fine. Two significant figures after the decimal. Okay, so this is how we will express the total value, right? Okay, so this is how we should, and the relative standard deviation, how much from one another is deviated, 0.26, and it is quite low, so it is acceptable as well that it is not that much deviated from one another relatively. So average weight of potassium perchlorate is 16.35 plus minus 0.04. Now, average mass and uncertainty. So for this case, mass of container with calibration of a B20 milliliter graduated pipette. We want to calibrate whether this pipette is delivering 20 milliliter of water or not, because everyone knows that with temperature increase or decrease, the volume of a material or liquid will be increased or decreased as well, right? So at our case, let's say this 20 milliliter pipette was calibrated when in the industry, when it was manufactured at 20 degrees centigrade. But in our lab, let's say it is not 20 degree, it is 25, 27 degrees centigrade, right? So whether it is still at 27 degrees centigrade, still it is delivering 20 milliliter or not. Maybe it is delivering 20.05 or 19.95, something like that. Probably it's just, I'm giving an example. So we want to know, we have to understand, or we have to be confirmed that whether our the pipette that we are using it for delivering 20 milliliter, is it delivering the accurate figure, accurate volume? So how do we find out what is the total value it is dispensing, this pipette, right? So first of all, we measure the mass of the water. We take the pipette, fill it up with the water, and then measure how much of the water it is delivering. The container, the empty container, this is the mass of container. Before we add water to it, it is 76.62 gram. But after we fill it up with the water, it becomes 96.55. Or what we can do is just put the beaker on the balance, electric balance, right? This is the electric balance. It is the panel, electric panel. It is giving us the weight, something like that. And we just we take the water in the pipette and then pour it up here, the empty beaker, which is on the balance, and see how much of the water it is delivering. And by this way, we see that it is giving us 19.93. Second trial, it is giving us 19.76. The third trial is giving us the third set of pipette. It is giving us 19.80. So average mass of water, all three trials, average mass of water, how much is the average mass of water we get? 3, but I mean all 3 sum up by divided by 3, so 18 point, it should be written here, yeah, 19.83 plus this, we have to find out the tolerance as well. So as I said, we have only 3 sets of data. But it is not feasible to do the standard deviation with only 3 sets of data. So what we do is average deviation. We do the average deviation, and by average deviation, the same way that we find out the average mass of that the value, and then we deduct it from each of the value. 19.93 minus 19.83. 19.93 is the first data, and then plus 19.76 minus 19.83. 19.76 minus 19.83. 19.80 minus 19.83. But the good thing is you will never get a negative value because this is mode. This is a mode. It doesn't matter whether you get a positive or negative, it will always become positive. The value will always become positive. So this is we will be using as a tolerance. We'll be using as a tolerance. So since 0.0666, so 0.07, it will be the tolerance. Now, in this way, we are collecting or gathering the data, right? We are gathering the data. How do we know that this data that we have just collected is good? Or we should be considering that data? It can be a mistake, right? It can be a mistake for us. Sometimes we will see suddenly that the value we are getting 19.5, 19.956, 19.58, 19.49. Suddenly it goes to 20.2. And then we are panicked that, why? What happened? Probably it is not our fault. Maybe it is the instrument fault. Maybe it is the other random error. But then we are panicked. Should we keep it? Should I still consider it in finding the average value, or should I just discard it? Yeah. So this to deal with this type of dilemma or doubt, there is a test that we can reject a data which is called outliner data by using student Q test. And the test is if the data is within twice the standard deviation of the mean, then it should be kept. If it is equal or more than twice the standard deviation value, it should be rejected. All right. So with a 95% confidence limit. So this is another term that we use for statistics. And we are not talking much about it, but from the Gaussian distribution, probably it will be a bit easier to understand. So this is a Gaussian distribution, right? So 95, if the data, the more closer this is the mean value, right? In between, this is a mean value. So the data, it is as we just saw in the accuracy and precision, it is very hard to get the dart hit at the center of the board. It is very hard, right? So if it is the mean value and getting a data here, the chances are low. All the data you get along this mean value or along the very precise value, the chances are low. Why it is low? Because there are random error. If not systematic error, there should be some random error, and then it is hard to get exactly every time, every single operation, the same value. So probably you will know more about it when you go to third year, fourth year. We have when you study the thermodynamics, there is an entropy. It says, okay, this is beyond the scope of our class now. If I start talk, I will not finish this. So anyway, so this is very hard to find a data along the mean value. So what we do is we just widen the scope, right? We just widen the scope. We just open the window a bit so that more wind or more sky or sun can come through, right? So if we open it a bit, like plus minus 1 standard deviation wide, then there is a chance that 68% time we will get the value along this area, in this area. 68% or 70% time we will get a value around this area. But if we just wide a bit more, which is 2 standard deviation wide in either side of that mean value, in a 95.5% time, all right, or more than 95% time, that we are confirmed that we will get a data or value along that. But if we want to get 100% time, we have to widen the whole, not the window, not the door, but we have to break down the whole wall. And that is not acceptable, right? We can open the window sometimes, but we cannot break the wall to get the sun in, right? We have to have the wall. So that is why just an analogy I'm giving, which is not an actual thing. So 95% time, it is, it is acceptable. So in a 95% time, it is the standard deviation should be 2. This is standard deviation is 2. So if within this range, the data is not in, the value of the data, that is the value, we don't get it, that means the data we can just strike out. We can just discard that value, that it is too wide to consider it is accurate. All right, so now the example is, it will be clear from the example that one student get the standardization values of 0.1, 0.1, 0.1012, 1014, 0.1012, 2116. So 12, 14, 12, 16. These are great. These are, we understand from the just looking at it that okay, these are close. But what about 0.21? It is suddenly it jumps up, and then I'm in doubt that did I make a mistake, or was there a problem? Should I keep or should I just discard it? Impulse is giving me that probably I have done a mistake. I should just throw it and don't tell anyone, right? My group has done it. Nobody else has get this type of data, so probably I'm wrong. So just don't tell anyone. Just throw it. No, probably you have done good thing. Who knows? So that's why we have to understand, or we have to do the student Q test. How do you do the student Q test? First of all, we have to get the average of all the values. So the average is 0.10146. This is the average. Do not round off at the very beginning. Round off only at the end of your operation. Round off only at the end of the operation, right? So if we just so yeah, now we get the average is 0.10146, and now we will do the standard deviation. The standard deviation, how do you do the standard deviation? All right, so this value minus this x minus x bar squared, and then plus this value minus x bar and squared plus so on this way, and then root over of this value minus, there are 5 sets of data, so 5 minus 1, 4 divided by 4. So by this way we'll get the standard deviation. The standard deviation value is 0.00374. All right. Now, if this data 0.1021 is within the plus minus twice the standard value. So if we get the twice the standard value of this data is 7.48 10 power negative fourth, right? So this value, what is that? 1.1021, it is within this value, right? It is within the plus minus standard deviation of this. So it should not be discarded. We cannot discard it from this so mean plus minus standard value. So what is the mean? Yeah, this is the mean plus minus 7.4848 times 10 power negative fourth, right? 10 power negative fourth. Oh my god. Okay, so plus minus. So if this value is within this range, then we should not discard it. And in this case, we see that it is within this plus minus twice the standard deviation, so we should not discard this value. All right. So here we see that average water, mass of water, calibration of 50 milliliter beaker, and then we can do it again, once again in that way. But since we can do the standard deviation here, but for our convenience, only 3 sets of data, we can do average deviation as well. And it should be okay because only three values are there. But if we have 5, then we should do the standard deviation, and it would be standard deviation is much more sophisticated, much more precise than average deviation. Combined uncertainty, and then after this I will stop for today. So I'll start next week the atom. So the real chemistry I will start next Monday, and which will be online as well. So combined uncertainty, the addition or subtraction. If there is a uncertainty, let's say that the value is x plus minus what should I get? A, right? Y plus minus B. So this is the uncertainty. So if we add it, these two values, x plus y or x minus y, this A and B should always be A plus B, never A minus B. The uncertainty will always be added, never subtracted. It can be x plus y. It can be x plus y. And then this is plus minus A plus B. Or it can be x minus y. And then the uncertainty is still plus minus A plus B. A plus B. So the uncertainty always increase. Uncertainty always increases, it never decreases. And there is a practical, we can show it practically. When I go back to lab, I'll show you. Please remind me how it always increase. Okay, where is my cursor? Okay, so but multiplication and division. If we do the multiplication and division operation on the values that is having uncertainty, what we'll do is it will be always added. It will always be still be added, but there are different ways that we can add it. We can add the percentage, or we can add the absolute value, right? So there are 2 ways that we can add the subtraction. So this is a perimeter. This is long and the width of a rectangle, right? The length and width of the rectangle. And the perimeter of the rectangle is added 3 plus 3 plus 2 plus 2. So the total value of the rectangle is this one, right? We have to add, then we only get how big it will be if we straighten it up. So how big it will be. So perimeter of the rectangle is 10 centimeter, but the uncertainty is added. Because of course we are adding this, we are dealing with this uncertainty, and we are not leaving it. We are bringing it here, and then we are bringing it here, and then we are bringing it here. So uncertainty always being added, and the total uncertainty becomes 0.20. But what about for other operation, right? What about for other operation? This is the uncertainty. We are adding it together, and okay, multiplication and division. So if there is mass and height and radius of a cylinder, right? Of a cylinder, I think, yeah, this is the cylinder. Let's say this is the cylinder. We have this is the height. This is the radius of the cylinder, and this is the mass. There should be some mass of it. So how will be the density? That we know that D equals m over v. Density or delta is mass over volume. Mass over volume is the density, right? So if we know the density, I mean, if we want to know the density, we should divide mass by volume. Then we will get the density. But for this case, let's say that we have mass of this one, and with the uncertainty of 0.5, and on the right side, this is a percentage uncertainty. This is absolute uncertainty. This is absolute uncertainty. That means the scale or the balance that we have measured, that balance has a 0.5 uncertainty limit value. That it always do 0.5 uncertainty. That means 165 0.16 5.5 to 165 6.5 until that. So this is the uncertainty of the mass, but for the percent uncertainty, this is 0.3% in relation. This uncertainty in relation to the actual value is 0.3%. So on the two sides, the percent uncertainty and the actual uncertainty, absolute uncertainty, both are given, right? Same way, height we have measured and we got the absolute uncertainty, and percent uncertainty, radius we get. So what is the overall uncertainty? Density, mass over volume, and mass that is given already, but volume we can find the for a cylinder that pi r squared h, right? That is the volume that it gives. So for those who wants to know, this is pi r squared h is the volume for a cylinder. So by this way, from this we get the volume. We get the volume of the cylinder, and then we get the total absolute value for this density. But it is not the same thing with that we should be reporting to our scientific community, and it should come up with the uncertainty. Okay, so uncertainty, there are two methods that we can measure. One is direct addition of the uncertainty, absolute uncertainty, or we can use the percentage uncertainty as well. So direct addition of the uncertainty is this is del rho over rho. That means small, that is that uncertainty in density. That is the uncertainty in density, which is we are looking for. This is what we are looking for, but this is the total density that we have already calculated. That is 171, right? 176, 177. This is 177. This is the total answer. This is the rho. All right. And then the mass of uncertainty. The mass of uncertainty is 0.5, and the total mass is 165.9. So 165.9, the total mass, and so on. For this is the how we should do the uncertainty. But for R, since R is squared was used in the In the formula, R squared was used. So this is twice it is added. Twice it is added or multiplied by 2. So this is how we will get, and at the final stage we just multiply with the total uncertainty from this side. It was rho here, the denominator. So then we get the total uncertainty. So this is the density. Total uncertainty is 0.09. Other way, method 2 is just a simple sum up with this percentage of uncertainty, but percentage of uncertainty probably most of the time will not be given to you guys. Okay, if you want to do this method 2, you have to find out the percentage uncertainty first, and then only you can use this method 2. And R squared, again, it is 1.9, but it has to multiply it by 2, or squared to you by, so that we can get the actual operation condition that we got. And then the sum of it, this is not the last stage. This is the percentage. Remember, this is the percentage. So in relation to the total density, what is the relation? What is the percentage? So 5.3 in percentage in relation to 1.7 is 0.9381. So this is the total uncertainty will be the same thing. So both way, whichever is easier for you, you can do it, no problem. But you cannot mix one into another one. If you are doing method 1, do method 1. If you are method 2, method 2. And this is the thing that you should be testing, or you should be practicing at home at your own time. Oh, another thing, I forgot to mention that it is not always this is the value or equation that you should have this type of or this many of the operation. You can have more. Okay, I'm not sure. Maybe it is del what we say, del omega over big omega. Okay, or maybe it is del plus del let's say A over big A. So it depends on how many factors you have included in it. It will all should be added up, and it may be only for 2 operations, just like the volume and the next slide that we have, the volume, rho, and mass for density of water as well you can find. So my point is, it will follow as many of the factors that you have in your operation. So dimensional analysis very quickly, and I think we have learned it in foundation, the dimensional analysis, and you guys are okay with that last time as far as I remember. But anyway, for a refreshing, please go through the slides. If you have any question, please let me know so that we can discuss. All right, so is there any questions so far today? I think we're out of time, 1 minute. All right, is there any questions so far? Hello. If no question, then okay, I'll stop it here today. I'll see you Monday, 9 a.m. Malaysia time. So yeah, take care, all the best, bye-bye.